is going to be Ashok Kutsovsky, who's going to speak about finite guarantees.
Okay. Yeah. Cool. Okay, so this is a talk about online linear optimization, actually. So let me just briefly outline the setting. So we have a learning algorithm that's going to play a sequence of t rounds. In each round, it chooses a point wt, which is allowed to be any point in some entire vector space. Then the environment presents the learner with a loss vector or a gradient, gt, and we suffer the linear loss of the inner product of gt and wt. Our objective is to minimize the regret, which is the total loss suffered minus the loss suffered at some benchmark point w star. So in contrast to the previous talk here, this is a point-wise regret that I'm talking about. So when I say I have a regret bound, I'm saying that this function of w star is bounded by some other function of w star for every possible w star. I'm not going to be taking the worst case bound over all w star in some domain because my domain is an entire vector space, and so this thing would always be infinity. That would be a bad idea. Okay? Great. So a lot of times when people come up with algorithms for this sort of thing, they'll say, oh, you know, I came up with a new algorithm, it's fantastic, it's optimal. And then, you know, a year later, somebody else will publish another paper and say, I have a different algorithm, it's also optimal, right? And you might ask yourself, how can this be? You know, how can we have two different, and the problem is, of course, that we're looking at these kind of point-wise regret bounds, right? And it's possible for two different regret bounds to be simultaneously optimal but kind of incomparable. And of course, what you would really like to have is one algorithm to rule them all, right? Like one algorithm that's actually optimal and is just as good as any of these all the time. Can we do that? Okay, so let's think about it. Oh, actually, before we think about it, let me give an example of how this might occur, right? So here are two algorithms that you can implement algorithms that do these two regret bounds. They're both relatively efficient, about as fast as gradient descent. And the first one is sort of two-norm adaptive. It has a regret bound that depends on the two-norm of the w star, the two-norm of the gradients, and then there's this parameter epsilon, which is the hyperparameter I'll mention later. You can similarly have a one-norm adaptive algorithm that's adaptive to the one norm of w star and the infinity norm of the gradients. In a d-dimensional space, it'll have some log penalty, and then again this epsilon parameter. So what is epsilon? It's a hyperparameter that the user might choose, and it represents the regret at the origin. I can't see where I'm pointing this, so I'm not going to point it. If you think about when w star is equal to 0, right, both of these bounds have a regret of epsilon, right? So it's saying that if you happen to start at the optimal point, you would sort of not be kicked around too much by noise. Okay, but the point is that these algorithms are both very, very good, but they're incomparable. The first one does really well when everything is sort of a little bit dense, right? If you're trying to minimize some function whose contours are sort of circular, then the gradients are kind of dense, and maybe your w star is a little bit dense. The first algorithm is great. The second algorithm does a little bit better when your contour lines are kind of diamond-shaped, and the gradients are like super, super dense, but maybe w star is a little bit sparse, right? Then the other one would be better. Which one should we choose? I don't know, right? It depends on your problem, and I don't want to know anything about your problem. I just want to, you know, give my software engineer some pseudocode and have them write that or something like that. All right. So how can we get both of them at the same time? I think the sort of knee-jerk reaction, well, what if I just average them, right? Like maybe the world is nice and made of butterflies, maybe p equals np, maybe I can just average all these things, right? Of course, the world is not so nice, right? If you try this, the first thing that'll happen is you're going to get a regret bound that is the average of the two, not the minimum. Too bad. All right, it's time to think some more. What if we use some kind of expert algorithm that will choose between the learners? I think this is sort of the first, like, okay, it's time to roll up my sleeves. We're going to do a lot of work now and design this really awesome expert algorithm. I'm not going to tell you that won't work. It might. And there has been some progress along these lines. There are some papers that, you know, have sort of meta expert algorithms that combine other algorithms to do things, but it's a little bit hard, and you tend to like, it's hard to keep track of all the adaptivity that was present in the original algorithms and keep that in the new things. We're going to do something quite a bit simpler. And we're going to use this tricky observation, which is that the previous algorithms I mentioned all have the property that their regret at the origin is epsilon, which is a constant. Okay, how can we use this? The algorithm is even simpler than just averaging. We're going to just sum. Okay? So we have two algorithms A and B that are outputting iterates WA and WB if I just give them the gradients GT. And my algorithm is just going to add up WA and WB and return that. Okay? It's really easy. Let's write down the regret. Well, the regret is GT WTA plus WTB minus W star, right, just by definition. And now we'll use the distributive property that everybody learned to know, I don't know, at some point, grade school. So then you get GT WA minus W star plus GT WB minus 0. Okay, Is that great? Who knows? Well, in the next line, we can see that the first sum is just the regret of the A algorithm at W star. The second one is the regret of the B algorithm at 0. And now we use the tricky observation, which is that the regret at 0 is epsilon, right? So we actually get the regret of the A algorithm plus this small additive constant of epsilon. And epsilon is not growing with time, right? So we didn't really lose that much over what the regret of the A algorithm would be. And of course, you can swap A and B in this analysis. Everything would be fine. All right, so immediately we can do something interesting with this, right? Like, for example, for any p norm, there exists an algorithm that has this nice sort of correct gradient adaptivity to both the W star and the gradients, where the gradients are measured in the Q norm. But this is for a fixed p norm. We can just discretize the space of p norms and then use this, do log d of this combination trick, and we'll get something that works for any p norm simultaneously, maintains all the adaptivity. Because if you notice in the previous analysis, I didn't actually care what the regret bound was, right? That was just some other analysis that you can do on your side, right? It'll just get the best of the two regret bounds. All right, so there's actually a better thing that we can do, which is that we can make a safety net algorithm. So let's suppose we have an algorithm that's really, really good sometimes, if you're lucky. But it's actually horrible if you're unlucky, right? Like maybe the gradients are, it's only good if the gradients are all equal to 1, right? It's really good at that. But if the gradients are ever 2, it's just going to do something totally random, right? So that algorithm is kind of bad on its own. But we can combine it with a conservative algorithm that's sort of just regular gradient descent or something like that that's somewhat sort of okay most of the time, or all the time. And then we'll have an algorithm that's sort of always safe because it's never worse than the safe algorithm. But if it gets really lucky, it'll be extremely good. And in fact, if you look at this carefully, it can actually be better than the sum of the parts in some sense. If you have the good parts of all the different algorithms sort of overlap properly, you'll end up with an algorithm that's kind of always in the good setting in some sense. And you can think of the classic adding the iterates technique as classic coordinate-wise updates technique as sort of a special case of this kind of thing. But we're going to talk about a different thing, which is optimism. All right. So in the sort of classic optimistic setup, you have this set of hints, h1 to ht. And if you know a bound on W star, you're in some sort of constrained setting, you can make an algorithm whose regret bound is small when the hints ht are good estimates of gt. Okay? So this is nice. But we can do a little bit better using the safety net technique. So I'll design an algorithm that's really, really good when the hints are correct. Okay? So if the algorithm basically plays along the directions of the hint vectors ht, and so if the hints are good estimates of the gradient, my algorithm will be extremely good. But if the hints are all perpendicular to the gradients or somehow bad, my algorithm will be horrible. All right? And I'm going to combine this with a backup algorithm that's sort of just generically okay. It gets something like Iterates guarantee. Okay? And then you'll end up with, you do a little bit of algebra, and you can end up with this bound, which is sort of non-obvious, and I'm not going to show you exactly how you do it, but it sort of speaks to the idea that you can get something a little bit more than the sum of the parts. So in particular, if you compare this bound to the previous classical bounds, it has two sort of interesting properties. One is that we're no longer constrained, so this works in the unconstrained setting. W star could be arbitrarily large. And the second is, of course, that the ht minus gt squared has been improved to have an extra minus ht squared involved. Okay. So to recap, we can add the predictions of all of these algorithms, and we'll get sort of a best of all worlds guarantee, right? And we can use this to make a safety net algorithm that can have good best case performance, even if the algorithm has poor worst case performance. And the safety net can be used for optimistic algorithms. I'm sort of hopeful that safety nets can be used for other things too. Like you could imagine having an algorithm that has some sort of sketching structure in it, and if the sketch is bad, it does horribly, but if the sketch is good, it does well, and you might be able to back it up. So I feel like there may be some more potential here. Okay, that's it. Thank you.
Any question?
Yeah, you can combine as many as you like. I mean, if you combine like k algorithms, you'll have a k epsilon additive. It'll look like the minimum of all the algorithms plus k times epsilon. So if you wanted, you could replace epsilon with 1 over k, and then you'll get a log k blow up.
What do you mean by tuning the value of normal W star?
For this guy? Yeah. So in these algorithms, the classic result, you sort of have, you're working in a constrained setting like the ball of radius r, and you sort of assume essentially that W star has radius r, has norm r. And so you're tuning the algorithm, the learning rate effectively of this algorithm is tuned to that value. Yeah.
Another question? So we don't, oh, yeah, sure.
Yes, this is linear optimization. Yeah, I feel like you might be able to do something, but it's something, the distributive property thing would be a little bit messed up, right? So like I'm not sure if it would work out so nicely.